Alright, we're going to start off by talking about probably one of the most common organic compounds, and that is the hydrocarbon. So the name says it all. Hydro for hydrogen, carbon for carbon. That means hydrocarbons contain only carbon and hydrogen. So organic molecules in general, some of them can have other elements like nitrogen and oxygen, but in the case of hydrocarbons, it's just C and H. So they can be separated as saturated or unsaturated, and there's 4 types of hydrocarbons. The first type is alkanes, and they're the only saturated hydrocarbon. Then there's alkenes, alkynes, and aromatic hydrocarbons, all 3 of which are unsaturated. So what saturated means? Saturated means it's holding as many hydrogen atoms as it possibly can. So the structure itself has as many hydrogens as possible. A good, simple way to think about saturated is there's no double or triple bonds. It's all single bonds. Alkenes, alkynes, and aromatic hydrocarbons are all 3 going to have either double bonds or triple bonds in their structures, and that's kind of what deciphers the names as well. So, for example, a saturated hydrocarbon, if it has just 2 carbons in it, so a saturated hydrocarbon would be like this, with as many H's as it possibly can hold. And so each carbon can have 4 bonds each. And so this carbon right here has 3 hydrogens and it's bonded to another carbon. And so it's holding the maximum possible number of hydrogens that it can. We can draw the same structure of 2 carbons, but let's say those 2 are double bonded to each other. Well, carbon can only have 4 bonds each. That means there's only room for 2 hydrogens. So it's not holding the maximum number of hydrogens. If it got rid of this double bond right there, we could fit another hydrogen there and another one there. So this is an unsaturated hydrocarbon. And that term saturation or saturated, you've probably read about it if you look on a bottle of oil or butter or margarine. It'll say things like polyunsaturated or saturated fats, and it's referring to that lack or placement of double or triple bonds. So unsaturated fats are fats that are going to have double bonds somewhere in their structure. And fats like butter and oil and stuff like that are just really long chains of carbon. And so if there's any kind of double bonds in them, that's what makes it unsaturated. A saturated fat, though, would be one that has nothing but single bonds. Saturated fats tend to be solids at room temperature, and that's because if we think about that carbon structure, so it's going to be a long chain like this with no double or triple bonds in there, which means they can line up in a nice straight line. And so when that happens, if you have, several of these molecules, if you've got a stick of butter, okay, it's going to have lots of these saturated hydrocarbons in it. And so all of these molecules then can line up in nice straight lines like this, and we can end up with those intermolecular forces in between all of those carbons in the separate molecules. And what intermolecular forces would those be between those carbon atoms? Yeah, if you said London dispersion forces, you are correct. Since these are both nonpolar molecules, that means the force that we're going to be feeling between those is London dispersion forces. So as opposed to a liquid hydrocarbon, so something that is unsaturated is going to have double bonds, and when those double bonds occur, it actually changes the shape, and so it's going to make it so it bends at different places. And as a result, if you have 2 of these hydrocarbons, they're going to be laid out like this, and so the intermolecular forces, well, they can only occur when they're touching each other. This carbon and this carbon right here, the 2 on the outer edges, they're not going to feel those intermolecular forces like these right here. As a result, a nice straight saturated hydrocarbon like this one is going to have London dispersion forces in a lot more places than this one right here. As a result, this would have a higher melting point, this would have a lower melting point. So this one would be more likely to be an oil, this one would be more likely to be a stick of butter or a tub of margarine. Alright, first let's talk about alkanes. So the generalized formula for an alkane is CnH2n plus 2. So this n, those would be the exact same number. So if you have an n number of carbons, you would have 2 times that number plus 2 number of hydrogens. So for example, methane, this first one right here, that would be C1, and then H's would be 2 times 1 plus 2, and that would be CH4. And you can see that there's 4 hydrogens around it. So you can figure out the number of hydrogens that need to be on a structure based upon its number of carbons. This second one over here, that would be 2 carbons, and since you have 2 carbons, that means you would need 2 times 2 plus 2 worth of hydrogens, and so that means C2H6 hydrogens. The reason that formula works is if you think about the structure, so they're always going to be saturated because these are alkanes, which means no double or triple bonds. So to get the maximum number of hydrogens, each individual carbon is going to need at least 2. So there's 2 hydrogens each, so that's the 2 times N. And then the 2 carbons on the end are going to need an additional hydrogen each to fill up its 4th bond. So you'd need another one there, another one there. That's the plus 2. So times 2 for each carbon to have its 2 right there, and then plus 2 for the 2 carbons on the end to have their additional hydrogen as well. So this first structure is methane. And this second structure right here is ethane. And the way you name them is based upon the number of carbons. And so this is going to be learning a couple more prefixes. So meth means 1 carbon. Eth means 2 carbons. This guy up here that I drew in with 3 carbons, that would be prop, would be the shorthand for that, and so that would be propane. So C3H8 is propane. So here's a list of all of the prefixes that you need to know. Some of these are going to be easier to memorize because they have familiar prefixes. Other ones you're going to have to just make some flashcards and learn them the old-fashioned way. So meth, as in methane, CH4, all of these structures that we've drawn over there, those are all alkanes. So the methane, this would be saturated. Ethane, this would be saturated. All of those would be saturated with hydrogens. And so the A-N-E at the end tells the reader that it is an alkane. Okay, we change the suffix based upon what type of hydrocarbon it is. So alkenes would be methene, alkynes would be methine. So since it's an alkane, methane. If you have 2 carbons, it's eth. If you have 3, it's prop. 4 is bute. Penta is 5, and that one should be easier to remember because if you think of the Pentagon, that governmental building, it has 5 corners on it, so pentane is 5 carbons. Hex, as in a hexagon, would be 6. Hepta would be 7. Octa, as in octopus, would be 8. Nona would be 9. And deca, as in decade, would be 10. So just make yourself some flashcards and memorize those. It's the same prefixes for alkanes, alkynes, and alkenes. So you just need to know those. The only thing that changes between the different types of hydrocarbons would be the suffix. What some of these are, so methane, that's natural gas. When you come to my classroom, we use the Bunsen burners. The gas that comes out is methane. It's CH4. It's very combustible because it doesn't need a lot of oxygen per molecule in order to combust. Propane, which is barbecue fuel. So if you have a gas barbecue at home, the gas that's going to be used in there is going to be propane. Lighter fluid, so any of those little flick lighters or safety lighters, those all use butane in there. Pentane and heptane are both solvents. So since both of these are non-polar molecules, they would both be used as non-polar solvents. So if you go to the solvent aisle or the paint cleaning aisle, paint thinner aisle at your hardware store, pentane and heptane are going to be a couple choices that are there, or mixtures of pentane and heptane that they use to dissolve different organic molecules or nonpolar molecules. And C6H14 and C8H18 are both components of gasoline. Octane is added into gasoline to make it flow better. Hexane is used in it just to burn, combust, and create that energy to drive your car. Okay, isomers. So a lot of you guys will end up taking organic chemistry in college. There's a whole entire sequence, a whole entire year of chemistry that's based on just organic chemistry because it's such a big branch of science. Isomers, though, is probably one of the most tricky things for students in that class. So we're going to give you kind of a head start, introduce you to the idea of isomers, so that hopefully when you get to that point, it won't be as hard for you. So an isomer is a compound that have the same chemical formula, but different arrangements of atoms. So you can write, if I were to give you a formula, like C8H, so 2 times 8 would be 16, plus 2 would be 18. C8H18, there's several different ways you can draw that out. Okay, you can do it in a long chain, you can do it with different branches. There's several ways you can draw something with 8 carbons and 18 hydrogens, just in different formats. And those different formats would be called isomers. Simpler hydrocarbons like methane, ethane, and propane, they only have one possible isomer. There's only one way you can write CH4, and it's with the carbon in the middle and the 4 hydrogens around the outside. If you're thinking, well, what if I do this right here? Problem with that is hydrogen can only have one single bond because it can only have 2 valence electrons. So this hydrogen in the middle, that is not possible. You can't have hydrogen with more than one single bond. So as a result, methane can only be drawn one way. Ethane, same thing. There's only one way you can arrange this. You can't draw 2 carbons and 8 hydrogens or 6 hydrogens any other way. Propane, 3 carbons and 8 hydrogens. Can't draw that any different way. So all 3 of these will only have one possible isomer. Once we get to butane, though, that's where we start throwing in the different isomers. So butane, but would be 4, so that means C4. How many H's would that have? Well, it would be 2 times 4 plus 2, so that would be 10 hydrogens. So let's look at some different ways that we can draw butane that have different formats, but still have 4 carbons, 10 hydrogens. The first one's just the normal way, which is a nice straight chain, so let's draw our 4 carbons. And then each of the carbons is going to get 2 hydrogens apiece. And then the 2 end carbons are also going to get another additional hydrogen. And so that makes 10 hydrogens and 4 carbons. Now, we could also take this same number of carbons, and instead of doing all 4 in a row, let's branch one of those carbons off like that. So see, we still have 4 carbons, just put out in a different way. And then if we attach the hydrogens, so remember each carbon needs 4 bonds. So this carbon right here on the end, let's give him 4 additional bonds, or 3 additional bonds, and those would all be to hydrogens because it's saturated. This carbon in the middle, it has 3 bonds already to carbon, so it just needs 1 more hydrogen. And this one on the end needs an additional 3 as well. And then this 4th branched off carbon, he's only got 1 bond, so it's going to need 3 additional hydrogens as well. Now, if we count the number of carbons, 1, 2, 3, 4, so we're meeting the C4, and then hydrogens, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're meeting the H10 as well. As a result, we have drawn C4H10, which is butane, in 2 different ways. These 2 different structures are going to have slightly different properties. You know, this one right here, it's going to have different London dispersion forces because it's a nice straight line. This guy right here with that branch, that's going to make them so they don't line up quite as well, and so that won't have the same London dispersion forces, but they're both butane. So to name these then, this straight line one, that's the normal way of drawing butane, in a nice straight line like that, and so the name ends up being normal butane. Yeah, real exciting, huh? And the way we would symbolize that, the way you would see it on a bottle, is N-butane. So N-butane means the normal way of drawing butane. Everything in a straight line, everything's got its hydrogens. And this other version of butane, it has this little group right here, which makes it different. So this version is called isobutane. Iso, the prefix iso, means the same, and since these 2 have the same structure, but this one's different than the normal butane, we call it isobutane, iso meaning the same structure. So there's really no way to look at the formulas and tell how many different isomers there's going to be. Really, you have to draw them out and take a look at the individual types to figure out whether or not it has multiple isomers and then what they're called. So iso means the same, normal means in, so the normal way of drawing it. Iso would just be something with the same structure that's drawn differently than the normal way. Another trick to drawing isomers is if we look at that N-butane that we've already drawn, you guys are going to see a lot that I just put dashes off of my carbons. Since in organic chemistry, everything or carbon bonds to hydrogen a lot, any time that there's a hydrogen, we usually just leave it off. So those little lines right there all mean that there's hydrogens. We don't draw them in because you should know that it has to be hydrogen. Since it's a hydrocarbon, all of those dashes represent hydrogens. So from here on out, I'm not going to draw them in. Another way of drawing butane then, if you were doing this at home, is you could draw it like that. That structure, though, is no different than this one right here. So both of these structures are still in butane. So the 2 structures are exactly the same because if you follow the carbons, all the carbons there are in a straight line, all of the carbons there are in a chain. Okay, and when they're in a chain like that, it doesn't matter how we bend it. Since bonds can rotate around single bonds, it's just these just kind of spinning around each other. but they're exactly the same. We could draw this same thing, C, 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 with the carbon going down like that, still the same structure. We could also draw it like this, and it's still the same structure because in all of these, the carbons are in one single file chain. It's just bending in different places, as opposed to the isobutane, which was C, 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 with the carbon branching off like that. If we were to draw the kind of carbon chain, it's a straight line there, then down there, and so this makes like a T shape, whereas all of these make a single line. So all three of these structures are exactly, or all four of these structures are exactly the same. Those would all be the N-butane. So watch out that you don't make just random drawings of the exact same thing. Be able to distinguish, are these carbons in the same form of line, and just draw them differently. Same thing, we can draw the isobutane as C, C, C with that fourth carbon coming off like that. And these two structures are exactly the same as well, because both of them create that T shape. So pentane has 3 isomers. Go ahead and pause the video here and see if you can draw out its 3 isomers. You should be able to name 2 of them, and then the third one I'll give you the name for when you resume the video. Alright, so pentane, that would be 5, so the formula would be C5H12, so 5 carbons, 12 hydrogens. The first way we can draw it is just in a line. So this line right there, since that's the normal way of drawing it, this would be in pentane. The next structure would also be 5 and 12, and in this case we have branched that carbon off, one of the carbons, the isopropyl, off one of the center carbons. So it doesn't matter where you put your little carbon chain if you draw this in. If you put it over on the next carbon over, that would also be okay. Just like that, so either one of them would be correct, or you could have taken that little group right there and put it down here as well. Any way you draw it, it's the same thing, just looking at it slightly differently. And since this one has the iso group coming off of it, this would be isoopentane. And then if you got the third isomer, it would look like this. So we end up with a tetrahedral structure around that center carbon. This has the same formula, so there's 5 carbons and there's 12 hydrogens around it. We're just drawn a completely different way than the other ones. And the name of this one would be neopentane. And neo means new. It's just a new version of pentane. Don't worry so much about the prefixes of naming these guys. If you know N is normal and iso means it has that little group branching off it, you should be fine. Okay, so when you drew out pentane for your third type, if you ended up drawing one of these structures as well, these are all isopentane. So these are all four the exact same structure. They have the line with the methyl or the iso group branching off. And so what that means is all 3 of these isomers are the exact same thing. It's just a different way of drawing it. So you can have that carbon coming off of him, down there. All 3 are isopentane. So after pentane, after C5, we start getting into a different naming strategy. So this is where the fun begins. So if you look at this compound right here, coming up with the name of this one is a little bit trickier, but it's an exciting type of tricky. So the step number 1 is to count the carbon atom in the longest continuous carbon chain. So if we go ahead and gander at this little molecule right here, this little hydrocarbon, your eyes might be at first drawn to this straight line right there as the longest chain. And that one's got 1, 2, 3, 4, 5, 6 carbons in it. But I will direct your attention to instead this chain right here, which has 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. So this chain would be our longest chain, and we want to use that as kind of the backbone then. So step number 1 is to find the longest chain and just kind of circle that or mark that. That's going to be the backbone of this here structure. And so 8 carbons, that would be octane. So kind of the basis, the backbone for this particular compound is octane. And then branching off of this octane, we have this single molecule right there, that single CH3. And so that's going to affect its name. But the basis for this one is going to be octane. So those little branchy groups, like we saw in that octane back there, we give them a name based upon how many carbons they have. So if it has 1 carbon, that's meth, and the branched off would be methyl. So the YL just means that it's a secondary alkane. So it's not the full long chain backbone group. Instead of it's a branching off group. So it's a secondary alkane group. So CH3, methyl, C2 would be ethyl, C3 would be propyl, and C4 would be butyl. And then isopropyl, we mentioned that before. Isopropyl would be a branch off like this guy right here. So it's got the 3 carbons coming off of it. So when you see this one, it's an isopropyl. If you see one of these 4, they're methyl, ethyl, propyl, or butyl. So then back to our octane chain. We said that the longest chain was octane. And then branching off of that is a methyl group. So we want to number our carbons so that the secondary alkane falls in the lowest possible number. So we could count our carbons in one of 2 ways. We could start here and go 1, 2, 3, 4, 5, 6, 7, 8, in which case this one right here would be 5. But if we start up here, it would be 1, 2, 3, 4, and we want to make our secondary group fall in the lowest number. So if we count it from this way, it would fall in the 5th. If we count from this way, it would fall in the 4th. So we're going to count from this way. And since the methyl falls on the 4th carbon, when we name this guy, we're going to indicate that in the name. So this is going to be 4-methyl octane. So 4-methyl octane means it's an octane backbone, an octane structure, with a methyl group on the 4th carbon. So 4-methyl octane. Isn't that a cool name? Okay, try this guy. First off, try and find the longest carbon chain, and go ahead and highlight that or draw that out. So there's lots of possible paths we can take here to make the longest carbon chain, but it ends up that the longest would be this carbon all the way down and then back over, because that structure right there will give us 1, 2, 3, 4, 5, 6, 7, making it a heptane backbone. And then you'll notice that this heptane has 2 methyl groups branching off of it. There's a CH3 right there and a CH3 right there. And so let's count so that we have the lowest numbers, and it turns out it doesn't matter where you count from. So this is 1, 2, 3, 4, 5, 6, 7. And our methyl groups fall on 3 and 5. And so we're going to name this one 3, 5 dash di, meaning 2, methyl. Sorry, that's kind of poor writing. There you go. So this one is 3,5-dimethyl heptane because we have 2, so dimethyl, 2 methyls on carbon 3 and 5, and the backbone is a 7-carbon chain, which makes it a heptane. So 3,5-dimethyl heptane. Make sure you put the comma between the numbers, and you put a dash between the numbers and then the name of the structure. But let's not let the fun stop there. Let's do another one. So try this one. Give it a shot. Find the longest chain, identify the secondary alkyl groups, number the carbons, name it based upon where those secondary groups fall and how many carbons those secondary groups have. Alright, for our longest chain here, we're going to go like this, and that's going to be 8 carbons. That makes the backbone of this guy an octane. And then for our secondary groups, we've got a 2-carbon chain right there. That would be an ethyl. And we've got a single carbon one there. That would be a methyl. Now we want to number, and if we started from this end, we wouldn't hit our first secondary group until we got 1, 2, 3 to 4. But if we start right here, we'd hit our first secondary group at 1, 2, 3. So we're going to start numbering here at that guy. So 1, 2, 3, 4, 5, 6, 7, and 8. And so that means the ethyl falls on 3, the methyl falls on 5. So the full-on name of this guy is going to be 3-ethyl 5-methyl octane. How sweet is that? 3-ethyl 5-methyl octane. And we just named that ourselves. Isn't that awesome? We are so much cooler than all those other people, huh? Alright, sorry to shift gears and change the fun, but now we're going to look at alkenes. So alkenes, they have a different formula for figuring out the formula. So an alkane would be CnH2 times N. So we don't have that +2 anymore, and that's because alkenes, E-N-E-S, all have this double bond in them somewhere. So this guy right here, it has 2 carbons. That would make it an eth group. And since it's an eth, and it's now an alkene, it's not going to be ethane, it's going to be ethene. And it's going to have 2 carbons, and then H, 2 times N, so that would be H4. This other one, that would be a prop group, since there's 3 of them, and since it has a double bond, it is propene. So that would be C3H6 because of that double bond. Okay. So here would be the names. You're going to notice that all of the prefixes stay exactly the same, eth, prop, but, etc. The only difference is all these have E-N-E, and that's because they are alkenes, E-N-E. So we just change the suffix, alkane, A-N-E, alkene, E-N-E. A couple similar alkenes, popular ones, produced by apples, so ethene. If you've ever looked on like the new packages of apples that are sealed, and you've got all of your little apples on the inside, there will sometimes be a little sticker out here that changes a certain color when they get ripe. What that sticker does is it measures ethene. So as apples ripen, they produce more and more ethene. And so when the ethene levels get high, it tells you the fruit inside is ripe. They do this with pears as well, that produce this ethene. They measure it that way. If you ever bought a pear at the grocery store, got home, tried to take a bite of it, and it was rock hard, well, if they measure the level of ethene that particular pear is releasing, they can tell you whether or not it's ripe without you having to squish around on it and ruin it for everybody else. And then propene, if you've ever seen that yellow plastic rope that they sell, that's made out of propene. So you can probably see a difference in how these things are used. Ethane would be a gas that we use for burning things. Propene is a rope. Okay, so let's take a look at some more isomers. Both of these are going to have the same structural formula. That's going to be C4H8, since it's butene. But there's 2 different ways of drawing this, and actually 2 different ways of naming it. So this first one would be 1-butene. That 1 up front tells us where the double bond is. And so here's our chain of 4 carbons, and the double bond falls between the first 2. And so we call that 1-butene. If we look at this other one, we still have 4 carbons, but now it makes kind of this Y shape. And as a result, with that Y shape, we have a 3-carbon chain right here. And so that would be propene, because it has the double bond with a 3-carbon chain. And then branching off of that 3-carbon chain, there is a methyl group, and that methyl group is on the 2nd carbon. So the name of this structure is going to be 2-methylpropene. 2-methyl because there's a methyl group off of the 2nd branch, off the 2nd carbon, and propene because the longest chain is a propene structure. This is still considered an isomer of butene because they both have the C4H8. Even though they're named completely different, they have the same structural formula, so they're both considered isomers of butene. This is a good chance to review single bonds and double bonds. So single bonds are sigma bonds, and sigma bonds are able to spin on their axis. So if you think of 2 carbons that are bonded by a single bond, that would be a sigma bond. So this one right here be a sigma bond. And if you just kind of visualize that in your head, you can rotate this bond either direction because it can spin on a single joint like that. Think of a toothpick wedged between 2 marshmallows. You can spin those marshmallows around because they can rotate very, very freely around that toothpick. However, a pi bond is going to prevent such rotation. So if we think now of 2 carbons that are double bonded to each other, that means it has a sigma and a pi bond. So we're going to have a sigma and a pi. It can't rotate the same way around those bonds. So think now of taking toothpicks and wedging them between marshmallows. You can no longer spin those marshmallows independently because they are forced together, so you can't rotate these guys different directions as a result because they're held together by those double bonds. What this means is we can introduce the idea of cis and trans isomers. No longer structures the same just because we spin them, because you can't spin a double or triple bond. Okay, these are 2 isomers of butene, so C4H8, and in this case, right here, we have C4, they're all in kind of this straight line, and the double bond is between carbons 2 and 3, so as a result this is called 2-butene. This second structure down here, it also has them in a single file line, and in this case the double bond is between 2 and 3 again, so it is also called 2-butene. But the shape of that single file line is different in this case. Since the compounds cannot rotate around this double bond, it's not like this one is just this guy spun in a different direction. In order for this guy to change to this guy, it would have to break that double bond, rotate, and then reform that double bond. So these two are not the exact same structure. This one is called a cis because it makes kind of that bowl shape. This one is trans because it makes that chair shape. So these are called in college typically boat and chair. So chair because if you think of this bottom structure, it makes a shape like a chair. You could very easily sit in that and drink a bottle of pop. This one up here, it makes kind of a boat shape because you could very easily sit in there and go fishing. So cis is boat-shaped, trans is chair-shaped. So cis and trans. And when I see you guys again in class, we'll go ahead and build some of these structures, and so then you can see firsthand, and it'll hopefully help you realize this if it's not making sense to you right now, why it is that double bonds can't rotate and have the cis and trans, but single bonds can rotate and do not have a cis and trans isomer. And now, alkynes. Alkynes have the structural formula of CnH2n minus 2. So alkynes, YNES, have triple bonds in them. So this first structure right here with the 2, that would be ethyne. And you're going to see that it's 2 and then 2n, so 2 times 2 minus 2, so 4 minus 2 is 2 hydrogens. And this last one with 3 would be a prop. So that would be propyne. So all alkynes have at least one triple bond. Here's a list of the names. The prefixes all remain the same. What changes is that YNE at the end, so ethyne, propyne, butane, etc. Only familiar one up here would be ethyne, which is used in welding. It's one of the welding gases. And finally, the aromatics. So aromatics, they're called aromatics because they typically have smells. A lot of artificial flavorings, artificial scents are made with aromatic compounds, and so the structures, there's something about them that fit very, very nicely into our nasal cavities, and so our body registers them as smells. So all of them have what's called a benzene ring. This is 3 different ways of drawing a benzene ring, and they all represent the same thing. So what this is it's 6 carbons in a chain, like we see up here, like I just drew, and each of those carbons is going to have an additional hydrogen coming off of it. And so that makes the C6H6. And then in order to have their 4 bonds each, all of these carbons are going to have a double bond every other carbon set. And so that makes it so each carbon has 4 bonds, which means it has a full valence electron shell. And we have those double bonds drawn in place. So this first structure right here that you see, that matches mine up here. Because we have the 6 carbons, each of those corners would be a carbon. The hydrogens aren't drawn in because you can assume there's hydrogens there. And these lines represent double bonds. So double bonds, when we have them like this in an aromatic ring, one of the things that gives them their properties is those bonds can actually hop around. And so this double bond might jump down there, which is going to bump that one over there, and that one right there. And if they make kind of that shift, that's going to create now this structure right here, where the double bonds fall right there. And in all actuality, in an aromatic, those double bonds are constantly cycling through, and so they're not staying in the same place the whole time. And so the way you'll see this drawn is just with a circle in the middle, which means there's double bonds between every other carbon, and it's just drawn in as a circle. So we call these benzene rings aromatics. We call all of them aromatics, even though not all of them smell. For example, Prozac. Prozac has 2 benzene rings in it, so it's called an aromatic, but it doesn't smell, apparently. Alright, here's 3 examples of aromatic compounds. So we have the benzene ring in all of these, and we've given them some different elements on them instead of just your typical hydrogen so that we can name these. So these are technically not hydrocarbons, instead they're aromatic compounds. So if we have NO2s, those are called nitros, Cls are called chloros, and Brs are called bromos. So nitro, chloro, and bromo. The way we name these then is we pick the first one on there, and so we're going to say this nitro is our first one, and so we're going to say it's attached to carbon 1. The next one is attached to carbon 2. And so the one way of naming this would be to call it 1,2-dinitro, so there's 2 nitros on 1 and 2, benzene, because it's a benzene ring. The second one, once again, we're just going to number them as 1, 2, 3. We start with the first one. If you were to do this backwards as 1, 2, 3, it'd be the same exact name, so it doesn't make a difference. So 1, 2, 3, which is why we then call it 1,3-dichloro, so 2 chloros on 1 and 3, benzene. And then this last one, if we count those carbons, 1, 2, 3, 4, doesn't matter which end we start with, we'd get the same name, 1,4-dibromo, 2 bromos, benzene. Then on the bottom, you're going to see a different kind of name. This is the more common way to name benzene rings. So ortho, meta, and para. Ortho means that the 2 functional groups, the 2 secondary groups, are right next to each other. So this one's called ortho-dinitro because the 2 nitros are right next to each other. They're in the ortho position. This one is meta because there's a space in between. So dichloro, 2 chlorines, are in the meta position with a space. And para means that they're on separate ends. So this is para-dibromo. The 2 bromos are on opposite ends. If we wanted to draw, meta-dinitro, we would just take off that nitro right there and move it down there. And that would make this now meta. And we could change this one over here to para by taking that Cl and then moving it right there. So ortho, right next to each other, meta, 1 space in between, para on opposite ends. And if we were to take this one right here and move it over 1 more space, that would make that one meta. And so once you cross that 6 o'clock mark, it's just going to restart with the meta, and that would be the ortho. And the last possible way to name benzenes is to also consider them as a functional group. So there's 2 ways we can name this one right here. If we name it just how we learned, it would be called ethyl benzene, because it's a benzene group with an ethyl branch coming off. So there's our ethyl right there, and here is our benzene ring. We don't call it 1-ethyl because it's only on 1 place, so of course it's on the 1 carbon. There's another way that we can name this, and that is a benzene because it's CH2CH3. And the other way that we can name this structure is, instead of considering the benzene as the main backbone of this, what if we were to consider the ethane as the main backbone? So instead calling this ethane, and then considering the aromatic ring, this guy right here, as a functional group, so as a secondary. So if the aromatic ring is instead considered a functional group or a secondary group, then we would name this one based upon the backbone of ethane, and since that aromatic ring is coming off, it would be phenyl ethane, because it's an ethane backbone with a phenyl branch coming off of it. And that's all for hydrocarbons. Sorry, this is a lot of information. It's hard really to edit this down. What you guys are going to be responsible for is definitely much smaller than what is in this PowerPoint or in this lecture. The best way to figure out what you're responsible for knowing is the practice sheets of organic molecules that I'm going to give you guys. That's what you want to practice with, and that will show you exactly what you need to know.